Okay, welcome back to another practical experiment at Gable Hall for the P2 physics course. This one is called waves in a solid. We've done waves on water before, waves in a liquid. This time we're looking at waves in a solid, and actually when they say solid they mean a string. Now the experiment we've got set up has a piece of string, a bit like a guitar string, which has been held tight by a mass that's hanging on the end there. That'd be very much like a guitar string where you've twisted the end to try and tighten up the string. And on this side, rather than us plucking the string with our finger, we've got a signal generator, a thing machine that's actually vibrating it for us. The beautiful thing of this is we can control the frequency of it. So by changing this device here, the signal generator, I can actually choose which frequency I want for this. And then currently, I've got, as you can see on here, a frequency of 23 Hertz. Now the point of this experiment is to try and show you what happens when you change the frequency to the wavelength of this string. So at the moment what you can see is, if you have a look, you can see my string is vibrating nicely, and actually what I've got here is one half wave. If you remember, if we were to draw out what a wave looks like, and I could draw a couple of waves on here, I'm going to draw two complete waves. We always mark on these diagrams the length of one wave. And you can mark it on in several places. The length of one wave is the distance for one wave to travel. If you have a look at what I've got going on here, if you can see closely, my string is vibrating. I've actually only got half a wave. I've only got one section there. So this, what we're looking at here, is half a wavelength. So what I want to now do is what happens if I change the frequency. So we go back to the same equation they always ask you to learn. P2, you must learn this equation. It will be questioned. It comes up in 2 out of the 4 practicals, and it is the velocity of wave is equal to the frequency times the wavelength. And as is always the case, we can pop it into the formula triangle, and when we do, because it's frequency times wavelength, the times bit always goes at the bottom and the velocity at the top. So I can work out whatever I want to do here. And what we should discover is that if I'm looking at the velocity of my wave on my string, and since I haven't changed the string, the velocity along that wave is always going to stay the same. What I want to know is what happens when I change the frequency. According to this, if the velocity stays the same, if the frequency goes up, the wavelength must go down. And in fact, if you double the frequency, the wavelength should halve. So here, you can see I've got my half wavelength. What I'm going to try and do now is double the frequency. So currently I'm on 23 Hertz because frequency is measured in Hertz. I'm going to double that to 46. So here we go, turn it up. Now you can hear the sound changing because as the frequency goes up, it's a higher pitched note. So I'm going to go all the way up to 46. Creeping up now. There's not much happening on the string at the moment, but if I get to 46, where I've doubled the frequency, let's have a look and see if I can see. Now if you look at our string now, you can see clearly, whereas originally the wavelength was the whole gap between the generator and where the string goes across the pulley, I had just one wave. You can now see clearly that I have two. So effectively what I've done, I've taken the wavelength and I've halved it, and the reason why it's halved is because I've doubled the frequency. So as the frequency doubled, the wavelength shrunk by half, and hence proving the equation that you have to learn for your exam. And that's the experiment you have to recognise. So this experiment helps prove waves in a solid and the wave equation. Thanks for listening.